Good day, students. In this clip, we're going to be going over how to resolve vectors by taking a look at an applications problem that involves bearing. Okay, so let's read the the question. It says a pilot is flying from LAX to JFK on a commercial jet, traveling 630 miles per hour in still air with a bearing of 83 degrees east of north. The pilot encounters wind at a steady speed of 30 miles per hour, blowing 6 degrees south of west. Part A, we have to make a sketch of the situation. So let's go ahead and sketch the situation here. So to draw angles, to draw vectors, we need a coordinate system. Let's place it on the origin. Alright, now this is our coordinate system. We can also place our cardinal points on our coordinate system. This is east, always the right side is always east, the top is north, south, and west. Okay? Alright, so let's see. The bearing of the aircraft was 83 degrees east of north. So if you're starting from north, you rotate 83 degrees from north towards the east. So it's going to look something like this, 630 miles per hour. Alright, and then this angle right here is 83 degrees. Alright, so if that's 83 degrees, we can figure out what this angle is. It is a complement of this angle right here, and this is going to be 7 degrees because these should add up to 90 degrees. Okay, so let's call this vector P for the plane. Alright, now next thing we're going to draw is the wind vector. The wind vector is blowing at 30 miles per hour, 6 degrees south of west. Alright, so if this is yeah, there's a typo here. This is supposed to be south of east. 6 degrees south of east. Alright, sorry about that. So let's say it's traveling, the wind is blowing 6 degrees south of east. Let's go ahead and make that sketch. So if you're going 6 degrees south of east, that means you're starting from the facing the east, and you're rotating 6 degrees, so slightly downwards right here, 6 degrees south of east. Okay, it's much shorter because vector W for the wind is only 30 miles per hour. Alright, so that's vector W for the wind, and that's vector P. So vector P is 630, and vector W is 30. Alright, and this angle right here is 6 degrees. Okay, now where would the resultant vector go? In order to do that, we're going to use the parallelogram law to create a parallelogram by translating this vector to the tip of the other vector, and then this vector to the tip of this vector right here. Okay, let's go ahead and do that. Alright, so I just copied vector P to the tip of vector W, and then we can copy vector W to the tip of vector P. So this is the wind vector on the tip of the plane's vector, and then that's the plane's vector on the tip of the wind vector. Alright, so this gives us a parallelogram. So the parallelogram rule tells us that the diagonal of this resulting parallelogram is the resultant vector. Okay, so resultant velocity vector is what we're looking at in this situation. So let's call this vector R, and that is the resultant velocity vector. Resultant velocity. Alright, so part A says to make a sketch and indicate what it looks like. So this is where it's going to be pointing, something like this. Now let's find the resultant speed. So let's find this velocity, the resultant speed, and the direction. Okay, So the magnitude of the resultant velocity will actually be our speed, since that's a scalar quantity. And we also have to find the direction of this vector. All right, so let's find the speed first. So to find the speed, we're going to have to add vector p and w first. So vector r, the resultant vector, is equal to vector p plus vector w, the planes vector plus the winds vector. The planes vector is 630 cosine 7, comma 630 sine 7. Okay, and then plus the winds vector, which is 30 cosine 6, comma 30 sine 6. Remember how to break up the vector into components. Let's look at that real quick. If you have a vector v, for instance, it has an x and a y component. All right, and the x component is found by taking the vector and multiplying by the cosine of the direction. That will give you the x coordinate of your velocity vector, and then the y coordinate will be the vector times the sine of the direction angle. Okay, so that's what we have here. I just basically wrote vector p and w using coordinate vector notation. All right, now to find out what these are, we just simply plug in these vectors into our calculators, and it will compute the sum for us. All right, so let's go ahead and compute the sum of the vectors. So for the x coordinates, we're going to have 630 cosine function 630 cosine 7 plus 30 cosine 6. And your answer is 655.14. 655.14. That's the x component of our resultant vector. The y component, we just simply add the y components of the individual vectors. All right, so all we just have to do is change our cosine to sines. Take that out. Change that. Sine. And then the other one, take that out. And then change that to sine also. Enter. So for the y component of our resultant vector, we have 79.9135. All right, so there goes the component form of our resultant velocity vector. All right, now to find the speed is basically going to be the magnitude of our resultant velocity vector. So speed, there's a scalar quantity, is going to be the absolute value of r. So how do we find the magnitude of a vector in component form? Let's review the formula real quick. So the magnitude of a vector is what you get when you apply the Pythagorean theorem to the component. So it's going to be the square root of the sum of the square of the component. So the x component of the vector square plus the y component of the vector square. If you take the square root of that result, that gives you the magnitude of the vector. Okay, so that's what we're going to do here. If we apply the formula I just showed you to this situation, what is that going to look like? It's going to be the square root of the sum of the squares of these vector coordinates or vector components. So it's going to be 655.14 square plus 79.9135 square. Okay, so we just plug that into our calculator. Okay, I did right here, and your final answer will be 659.996. So it's going to be approximately 659.996 0.996 miles per hour. Okay. All right. We asked to find the speed and the direction. So direction. How do we find the direction of a vector? So let's call that theta of vector r. To find that, all we simply do is we're going to take the inverse tan of the components of r. The y component of r divided by the x component of r. That will give us our direction. Okay, so this is the first component is the x component of vector r, the velocity vector r, and then this second component right here is the y coordinate of the velocity vector r. Okay, so to get the direction of the vector, we're going to compute the inverse tan of 79.9135 divided by 655.14. Okay, so let's put that in our calculators and see what the direction of the vector is. So we're going to have the inverse tangent. Let's clear that first. The inverse tangent of, I'm going to pull my answers, 79.9135 divided by the other answer we got. And our direction is going to be 6.9545. 6.9545. So let's write that down. So theta, the direction of vector r, is 6.9545 degrees. Okay, so if we wanted to describe the vector as a rotation from the northward direction, let's say if your rotation or direction is 6.95 degrees, all right, and if I wanted to use vector, if I wanted to use bearing, this is 6.95. Now, if I wanted to describe this from a north standpoint, how many degrees rotation from the north is 6.95 from the east? So to get the direction, the bearing from the north, we'll just simply subtract 180, subtract our answer from 180, right? So 180, try that, 180 minus our answer, so 1. So we're going to get, see what we get, 173 point, actually, let's see, we're supposed to subtract it from 90 degrees, not 180. Subtract from 90, sorry about that. So we're going to subtract it from 90 degrees to get the bearing. So it's going to be 83.0455. Let's see, where were we to round it up to? No indications here. All right, so we're just going to use 83.0455. Okay, so this is our direction, but our bearing, let's write this down, is going to be 83.0455. Okay, so what is the bearing here? It's going to be 83.0455 east of north. Okay, so let's write down our answer. So the resultant velocity, the resultant speed is 659.996 miles per hour, and the direction, using bearing format, the direction is 83.0455 degrees. Good day, students. In this clip, we're going to be reviewing an example on using the law of cosines to solve real-world application problems. All right. So let's take a look at question number 1. It says island A is 280 miles from island B. A ship captain travels 180 miles from island A and then finds that he is off course and 150 miles from island B. What angle in degrees must he turn through to head straight for island B? Round your answer to 2 decimal places. Alright, so to get us started, let's identify or locate island A and B somewhere on our grid. Alright, so let's say island A and B are located on those 2 points. In the first piece, we're told that the distance from island A to B is 280 miles. Alright, so let's draw that segment and put in the distance of separation between them, 280. And the ship captain originated from island A and headed 180 miles to some direction before he came to the realization that he's off course. Alright, so let's say that this is a point somewhere here where the captain realized that he's off course. How about we call that point C? Okay, now we can create a triangle like this. So he traveled 180 miles before he realized that he's off course, and he found out that he's off course by 150 miles. So 150 miles is how many miles he is away from his destination. Alright, so it says what angle must he turn through to head straight for island B? So his initial direction was from AC, was something like this, heading in that direction, and he was going off course. So the question is, how many degrees must he turn to be heading right back to his correct destination, which is B? So this right here is the angle that the ship must rotate in order to find in order to head back to the right destination. All right, we noted that this angle is a supplement of angle C, so all we just have to do is find angle C and subtract it from 180, and that will be the correct answer. All right, so let's go ahead and find C. Now what kind of triangle do we have here? This is an SSS triangle because you were provided with 3 sides. So if you have 3 sides for SSS triangle, you have to use the law of cosines in order to solve for any of the angles. Alright, so we have SSS situation or SAS situation. These triangles, you use the law of cosines. Alright, now the law of cosines formula that I'm going to use here is the one with the big C in it. So we're going to use the formula C squared is equal to, let's call this A, opposite uppercase A, let's call this B, opposite lower uppercase V, and let's call this C. Alright, so the formula is going to be C squared equals A squared plus B squared minus 2AB cosine C. Alright, now let's put in the angle measures. We have 280 squared equals 150 squared plus 180 squared minus 2 times, let's see, 2 times 150 times B is 180 cosine C. Alright, so let's get cosine C by itself. To get cosine C by itself, all we just have to do is subtract these 2 squares from both sides of the equation. So we have 280 minus 280 square minus 150 square minus 180 square, and then we're going to divide both sides by 2 times negative 2 times 150 times 180. So let's go ahead and do that. If we divide both sides by that expression, it's going to shift to the other side of the equation. We have negative 2 times 150 times 180. Okay. So let's plug this into our calculator, and then we'll take the inverse cosine to figure out what the value of angle C is. Alright, so let's go ahead and do that. We'll have, let's clear this. So we're going to have 280 squared. Be sure to group the numerator in parentheses since you have multiple terms being combined with each other there. Minus 150 squared minus 180 squared. And that entire expression divided by -2 times 150 times 180. And the answer is going to be -43519. Alright, so let's write that down. That's going to be -0.43519. Alright, let's get angle C by itself. To accomplish that, we'll take the inverse cosine of both sides. So C is the inverse cosine of -0.43519. Let's put that in a calculator and see what we get. So we have the inverse cosine of the answer, previous solution, and we have 115.797. Alright, so angle C is 115.797. Now the angle that we have to rotate to get back on course is a supplement of 115.797. Alright, so let's call this angle theta, what we need to turn in order to get back on track. Let's call it theta. So we have theta, wrong color, theta is equal to the measure of angle 180 minus the measure of angle C, 115.797. Alright, let's put that in our calculator and see what we get. So 180 minus our previous result, and the answer is 64.2. So let's write that down. Theta is approximately 64.2. Alright, so what does this answer mean? What is the meaning of this answer? It means that the ship has to turn 64.2 degrees. 64.2 degrees, actually technically should be negative 64.2 degrees, but 64.2 degrees to the right in order to be back on course, okay, to the original destination of B, to be back on course. Alright, so let's see how that value or solution looks like in the diagram. So this is the angular rotation that the ship must undergo in order to be back on track, and the value of theta, like we found out earlier, is 6. Good day, students. In this clip we're going to be going over some examples reviewing the resolution of vectors. So let's take a look at the first example. It says a force of 65 pounds acts on an object at an angle of 30 degrees. A second force of 70 pounds acts on the same object at an angle of -55. In a sketch of this situation and resolving the vectors, let's go over some formulas real quick. Let's say you have a force F, and I wanted to express this force in a component form. It can be written as a coordinate. So you have F in the x direction, comma, F in the y direction. Okay? How do you find the x and y components of this force? Assuming the direction of the force is theta, then we can simply find the components of this force by evaluating F cosine theta for the x component or the horizontal component, and F sine theta for the y component or the vertical component of the force. If you want to find the magnitude the magnitude of the vector, magnitude of f. The magnitude of f is written as the absolute value of the vector, absolute value notation, but this is known as the norm or the magnitude of the vector. And this can be evaluated using the Pythagorean Theorem, where the a and b are the x and y components of the vector. So f of x squared plus f of y squared. If you want to find the direction theta of f, the direction is simply the inverse tan of the y component divided by the x component. If you think about SOHCAHTOA, tan is opposite or adjacent. So in this situation, this is like the opposite, and this is the adjacent. All right? Okay, let's take a look at the problem now. So it says 65 pounds is acting at an angle of 30 degrees. So what we're going to do is let's assume that the object is sitting on a coordinate system, and the object is right on the origin. All right, so let's see. So the first one is 30 degrees and it has a magnitude of 65 pounds. So F1, okay? So call this F1. F1 is 65 pounds and has a direction of 30 degrees. Remember, when you rotate counterclockwise, it's positive, all right? The next vector is 70 pounds, second force, and is acting at an angle of negative 55 degrees, all right? It's going to be somewhere down here. Remember, when you're graphing a negative angle, you're going to be rotating in the clockwise direction, all right? So this angle right here is negative 55 degrees, and the force F2 is, I forgot, I think it's 70, right? It's 70 pounds, right? So 70 pounds. Okay, now that we have the vector sketched, let's use the parallelogram rule to find the direction of the resultant vector. In order to do that, what we'll do is we're going to just create a parallelogram. Alright, so the resultant vector, after constructing your parallelogram by drawing the two vectors on the tips of the other vectors, this diagonal right here from where the two tails originates, the origin to where the two tips meet, will be your resultant vector. Okay, so this vector right here is going to be, let's call it vector R, our resultant vector, and it is basically F1 plus F2. Alright, F1 plus F2. That is what we are supposed to find. Okay, so in order to easily find F1 plus F2, I'm going to express these two in component form, and then just simply add the components to find vector R. Okay, so let's start with vector F1. F1 is equal to let's write it in component form. 65 cosine 30 degrees for the x component, and 65 sine 30 degrees for the y component. And then F2 is equal to 70 cosine negative 55 for the x component, and 70 sine negative 55 for the y component. Alright, so let's write this in decimal form so it's easy for us to find the sum. Let's use our calculators to find out what these are. So we have, let's see what we have here. And make sure your calculator is in degree mode because our angular measures are in degrees. Okay? Alright, so we're going to start with 65 cosine 30 for our x coordinate of F1, and then 65 sine 30 for our y component of F1. So we have 56.2917, 56.2917, comma, 32.5. Now for our y, for vector f2, we're going to do 70 cosine negative 55. Alright, see what that is. And do the same thing, 70 sine, I did the inverse sine, 70 sine negative 55, alright? And then your answer is going to be negative 57.3406. Okay, so let's write it down. For our vector f2, we have 40.1504, and then the y component of f2 is negative 57.3406. Alright, now to find the resultant vector r is simply going to be f1, vector f1 plus f2. Okay, how do we figure that out? We're just simply going to add these two vectors to each other to get our final answer. Alright, so let's go ahead and compute what the sum is. So to find that out, we're going to do 56.2917 plus 40.1504, and we have 96.4421. Let's write that down. 96.4421. That's the x component of our vector. And then for the y component, let's do that. We're going to have 40.1504 plus negative 57. Actually, let's do that again. We're doing 32.5 plus negative 57.3406. Alright, so that's our y coordinate of the y component of our resultant vector. So that is, let's write that down again, negative 24.8406. Alright, now let's find the magnitude. To find the magnitude of this vector, magnitude of vector r, that's simply going to be done by taking the square root of the x component of vector r squared plus the y component of vector r squared, the square root of the sum of the squares. All right, so that's simply going to be the square root of the sum of the squares of these two components. So 96.4421 square plus negative 24.8406 square. Okay, let's go ahead and evaluate that. We're going to have the square root of 96. Let's just go ahead and copy down this answer just to save time. So copy that down, square plus this other answer, square, and our answer is 99.5898. Alright, so the magnitude of vector r, the resultant vector r, is 99.5898 pounds. Alright, now let's find the direction. Okay, the direction, let's call it theta. Direction, theta of the resultant vector r is going to be the inverse tan of the y component of vector r divided by the x component of vector r. Okay, so that's simply going to be the inverse tan of the y component right here, which is negative 24.8406 divided by the x component, which is 96.4421. All right, let's go ahead and evaluate what that expression equals. This kind of looks like a 4. Let's fix that. 4421. All right, so if we do compute the quotient in our calculators, we have negative 14.4437 degrees. All right, so theta equals negative 14.4437 degrees. All right, so let's write down the meaning of our answer. What our answer means is that the resultant force has a magnitude of 99.5898 pounds, and a direction of negative 14.443 degrees. All right, so let's apply our answer to our sketch right here. So this is the 99.98. Is that what we got? No, 0.558. 99.58. This is the sum of the two vectors. And the direction is right here. The direction is this angle that this vector r has. So this angular measure right here is what did we get? Negative 14 degrees. All right, negative 14.44, I think, degrees. That's the Good day, students. In this clip, we're going to be going over some examples that will help you review how to generate graphs of rational functions. So let us take a look at question number 1, where to determine the equation of any vertical asymptotes and the values of x for any holes in the graph. Okay, so how do you find the holes in vertical asymptotes? We're going to start out by writing down the procedure for finding each. So to find the holes, you set factors that cancel out, to 0, and then solve. So if you have a rational function, you factor the numerator and the denominator. Any factor that's common in the numerator and denominator that you can cancel out are the equations that you use to solve for the holes. Okay. All right. So let's talk about the vertical asymptotes. How do you find the vertical asymptote? To find the vertical asymptote, you're going to set denominator factors. Set denominator factors. Set denominator factors that do not cancel out. Set those ones equal to 0 and solve. Okay, so the ones that cancel out tell you your holes, and the ones that do not cancel out tell you your vertical asymptotes. Just for your information, holes are also known as your removable discontinuities. All right, and vertical asymptotes are also known as your poles or infinite discontinuities. All right, so let's go ahead and find the holes first. So to determine what the holes are, we have to determine what factors cancel out. Okay, so write down the numerator and the denominator. Now, what does the numerator and the denominator have in common? In order to answer that, we have to factor out the denominator, okay? So let's use the AC method here. AC is 10 and B is -7. Two numbers that work here are -5 and -2. We do not need to factor by grouping here because A is 1. Alright, so this is equal to x minus 5 divided by x minus 5 times x minus 2. Now examine this function. What do you notice? You notice that x minus 5 is common in the numerator and the denominator, so it can be cancelled out. So x minus 5 goes here 1, x minus 5 goes here 1. So whichever factor cancels out, that tells you your wholes, alright? So to find the wholes, we're going to set the factor that cancels out equal to 0 and solve. You add 5 to both sides, and you have x equals 5. There goes your whole. And then to find the vertical asymptote, all you do is you look at the denominator and extract factors that did not get cancelled out. Okay, the reduced form of the polynomial expression, you just set the denominator of that polynomial to 0. So in this case, x minus 2 doesn't have any common factor in the numerator, so we just extract it. So equal to 0 and solve x equals 2 is our vertical asymptote. Alright, so let's see, where's the answer? Wholes 5. So it cannot be A or B. Vertical asymptote of 2, so our answer is option letter C. Alright, let's take a look at question number 2. We have a transformed rational function here, f of x equals -7 over x minus 6, and we're asked to sketch the graph of the resulting transformed function. Now we'll take a look at the standard parent function for rational functions. F of x is equal to 1 over x. There are some interesting things that we can determine from this function. First of all, we can clearly see that the vertical asymptote is going to be 0, so let me create my coordinate system here. So let's see, coordinate system, there goes my x-axis and my y-axis. Now for the parent rational function, f of x equals 1 over x, the vertical asymptote is equal to 0 because you set the denominator x equals 0, right? And then it's already solved. Nothing cancels out here, so the only factor in the denominator that remains is x equals 0. So we have a vertical asymptote right on the y-axis, so you have a vertical asymptote right here. And then in this function, you also have a horizontal asymptote of 0. You have that because it is bottom heavy, and at infinity or negative infinity, this whole expression collapses to 0. So you have another asymptote here, a horizontal asymptote. Alright? Now, the nature of this graph is as follows. From the left side, you start from the asymptote, and your horizontal asymptote, and head towards negative infinity. And then on the right side, you start from infinity and head towards your horizontal asymptote. Alright? So it's good to memorize the way this function looks like. Alright? This is the orientation of the parent function. Now, if you look at this equation, this is a transformation of this. You notice this negativity means that this function is simply reflected along the x-axis. So if you want to have f of x equals -x, it's -1 over x, it's going to have this appearance with each portion reflected to the opposite, to the coordinate above or below. So this one goes up here to there, and then this portion right here goes to here. This negative reflection does not have any impact on the asymptotes, alright? Now how about this 7 right here? This 7 basically means the dilation along the y-axis. It just stretches it up or down vertically. So that doesn't have significant impact on the look of the graph. But this x minus 6 is important. This x minus 6 is a shift along the axis. All right. So since x minus 6, we're going to do the opposite. That means you're going to shift 6 units to the right. So f of x equals negative 7 over x minus 6 is a dilation of a factor of 7 along the y-axis and a shift of 6 units to the right. So it's going to look something like this. So let's say you shifted it 6 units to the right. Let's say this is 2, 4, 6. So you shifted 6 units to the right, then your vertical asymptote will also move along with that. It will be shifted 6 units to the right. Your horizontal asymptote remain unchanged since there is no translation in the vertical direction. All right. Now your function that's being reflected and dilated by a factor of 7 is going to look something like this. Remember, the dilation is not that significant. It doesn't significantly alter the appearance in the sketch. This is not perfect. It's just a sketch. So this is what your graph should look like. All right. Okay, so let's take a look at this right here. If you wanted to do it in a different way, you can solve for the solve for the vertical asymptote. How do you solve for the vertical asymptote here? What you do is you set the denominator equal to 0, and you solve, and you have x equals positive 6. So you go down to positive 6, 1, 2, 3, 4, 5, 6, and you draw your vertical asymptote. All right? And then you look at this function and you say, oh, it's bottom heavy, so you know that your horizontal asymptote is going to be 0, because any bottom heavy rational function has a horizontal asymptote of 0. All right? And then ideally, a rational function of this nature will look something like this. You have one here and another here. I'm sorry, you have one down here and then another here, but with this minus, it gets reflected. So instead of having a portion of it down here, you have a portion of it up here. As you approach this vertical asymptote, you tend towards infinity, and then down here, you start from negative infinity and head towards your horizontal asymptote like that. And you can definitely verify the accuracy of your graph, of your sketch, by using a calculator. A TI-89 or any graphing utility should suffice. So I'm going to input this function into my graphing window and then see if it matches what I have here. So negative 7 divided by, now since we have two terms in the denominator, we have to group it with parentheses, okay? So x minus 6. Close that. Enter. All right, let's graph it. Diamond F3 is the graphing for TI-89 titanium. Let's see. And then over there. All right, you can see that at 1, 2, 3, 4, 5, 6, we have a vertical asymptote. So this shows that our answer is in. Good students, in this part we're going to be reviewing the trig identities. So let's take a look at question number 1. We're to find sine A minus B, given that sine A is 2 over 5, with A between pi over 2 and pi, and cosine B is 4 over 7 with B between negative pi over 2 and 0. Okay, so we need to start off by writing down the identity that can help us determine what we're working with here. So we have to find sine A minus B. So what trig identity are we going to use here? Well, we have the sine and two angles, alpha and beta, separated by minus. So we're going to be using the difference identity for sine. So the difference identity for sine is sine alpha cosine beta minus cosine alpha sine beta. Okay, so this is the difference identity for sine. Let's apply it to this formula right here. So if I apply to this formula, sine A minus B is going to be sine A cosine B minus cosine A sine B. Okay, all right, so let's see what we have. We're given sine A, we know sine A and we also know cosine B, but we need to find cosine A and sine B. Those are the two we need to find. All right? Okay, so we can make a list up here of the things that we have. We have sine A is 2 over 5, and then we also have cosine B being 4 over 7. So we have to find the other two. Okay, so let's start off by looking for, let's find, how about we find cosine A first? Now, how do we find cosine A? Well, we can use the Pythagorean identity to find cosine A from sine A. The Pythagorean identity I'm going to use is cosine A equals plus or minus the square root of 1 minus sine square A. Okay? If I plug in the value of sine A in here, I'll have plus or minus the square root of 1 minus sine square A is 2 over 5, so when I square that, it's 4 over 25. If I find the LCD of these two, I'll have 25 over 25 minus 4. So we'll have plus or minus the square root of 21 over 25. Okay, because, 25 minus 4 is 21. And then we can simplify that further into becoming plus or minus root 21 in the numerator over 5. Now, is this plus or minus for cosine? Well, we need to consider the interval that this angle resides in, the quadrant, sorry. So A is between pi over 2 and pi. Let's determine what that is with a sketch using our quadrants. So let's see. We have pi over 2 up here, pi over 2, and this is pi. And this is where angle A resides, okay? This is where angle A is. Let me not put a letter there because that might be confusing. So let me just call this pi. And then we're going to see how we can determine the sine of the angle, okay? So this is the angle under consideration here. And we remember that all students take calculus. This S means that only sine and its reciprocal cosecant are positive in this quadrant. So this is neither both of them. So it's going to be negative. So we can conclude that cosine A is negative root 21 over 5. Okay, let's put that up here. Cosine A equals negative root 21 over 5. Now the next thing we have to find is sine B. Now how do we find sine B? We find sine B by applying the same identity, the Pythagorean identity, but we're going to have cosine and sine interchanged with one another. All right? So sine B, using the Pythagorean identity, is plus or minus the square root of 1 minus cosine square B. Okay? So that's another identity. So let's evaluate what this expression is when we substitute the value of cosine. So it's going to be plus or minus 1 minus cosine B is 4 over 7. So if we square that, it's 16 over 49. Okay, and then if you multiply both sides, you have 49 and 1. And then if you subtract 16 from 49, we get 33. Okay, so this becomes plus or minus the square root of 49. Let me just write it so you see minus 16 over 49. So that becomes plus or minus root 33 over 49. And then when we break it apart, it's plus or minus root 33 over 7. So the question now is it positive or negative? Sine B, that is. So to answer that question, we just have to determine what quadrant this angle lies in, and then figure out what the sine is, all right? So angle B is between negative pi over 2 and 0. So negative angles are determined by rotating clockwise. So this is negative pi over 2, and this is 0. This is where our angle resides. And we know that all students take calculus. What this C means in quadrant 4, where our angle resides, is that only cosine and secant are positive. So since this is sine is not cosine or secant, that means it's going to be negative. So this will be negative root 33 over 7 for sine B. Okay, so we have everything that we need. Alright, so let's go ahead and figure out what the answer is. So sine A minus B is equal to sine A. Sine A is 2 over 5, and cosine B is 4 over 7. So let me write it again so we don't forget. Sine A cosine B minus cosine A sine B. Alright, so sine A is 2 over 5 times cosine B, which is 4 over 7, minus cosine A. Let's see, what's cosine A again? Negative root 21 over 5. Let's put that in parentheses. Negative root 21 over 5 times sine B, which is negative root 33 over 7. Okay? If we multiply them together, we're going to get 8. Now these two minuses multiply to give you a plus. So let's do this. This is 8 over 35 minus, if we multiply these two radicals together, we just multiply the radicands. It's going to be root 693 over 35. Okay, so that becomes 8 minus, denominator is 35. So let's look at the options that we have. Oh, we can see that the answer is option A because that's the only one with 8 minus. But let's go ahead and show that this reduces into 3 root 77. All right, so let's break that down on the side here. Simplify radicals. We already know how to do that. Let's see. 3, if you add these digits together, 3 goes into them. So 3 goes here. 3 goes into 693, 2, 3, 231 times. And let's see, 3 plus 1 is 4, 4 plus 2 is 6, so 3 goes here also. Since 3 goes into 6, 3 goes into 21, 7 times. And then 21, another 7. 7 can be broken, 77 can be broken down into 7 times 11. All right, so these two repeat themselves, so we can break out as 3. And the simplified form of root 693 is 3 root 77 because these two stay behind, okay? So we can see that our final answer is 8 minus 3 root 77 over 35 as the value of sine A minus B, all right? Which is option letter A. All right, let's take a look at question number 2. This involves the use of the unit circle or the knowledge of the value of your trig ratios. So let's evaluate cosine pi over 12. Now there are two ways of doing this. You can work with radians or you can express it as degrees. Okay, I'm going to work with radians here. So let's go ahead and do that. Cosine pi over 12. Now cosine pi over 12 is an uncommon angle, in the sense that this is an angle that does not show up on your unit circle. So can I express this as a sum or difference of two common angles? All right, so let's work with pi over 12. So I'm going to pick two numbers, multiples of pi that add or subtract to yield pi, and have a common factor or our factors with 12. So we can use 4 pi minus 3 pi. And both of them go into 12 over 12. And then we can reduce this into 4 pi over 12 minus 3 pi over 12. Okay, and then reduce this becomes pi over 3 minus, and this becomes pi over 4. All right. Now this is 60 degrees and this is 45 degrees. So if you wanted to use degrees, this would be 15 degrees, and then you can just use 60 minus 45. It makes no difference, all right? So we know what we are doing now. We have cosine pi over 12 is equal to cosine pi over 3 minus pi over 4. Okay? All right. Now, we're going to determine what identity we're going to be using here. So since there's a difference and there's a cosine, we're going to be using the difference identities for cosine. So cosine alpha minus beta, if you remember what it is, it's cosine alpha cosine beta plus sine alpha sine beta. So for the cosine difference identities, the trig pairs are the same, cosine and sine, and the sign is opposite, all right? So if I apply that here, I'm going to have cosine pi over 3, cosine pi over 4, plus sine pi over 3, sine pi over 4. All right? Now we're going to take a look at our unit circle. Okay, if you remember what it looks like, that's fine. We have two angles here, alpha. Alpha is the first one. Alpha is pi over 3, as you can see here. And beta is pi over 4. Now the unit circle, pi over 3, has x and y coordinates. The x coordinate for pi over 3 is 1/2, and the x coordinate is 1/2, and the y coordinate is √3 over 2. Okay, and then for pi over 4, it's √2 over 2 and √2 over 2. All right, so now let's see what we can do here. We can break them up. So we can partition it like this. All right, so what we have right here is this little trig table of trig identities. So the x coordinate we know is cosine, and the y coordinate we know is sine. All right, so we can use this little chart of common trig angles to find out what these the value of these expressions are. So let's go ahead and apply it. Cosine pi over 3 is the x coordinate of this, which is 1/2. Cosine pi over 4 is √2 over 2. As you can see here, cosine pi over 4 is √2 over 2, plus sine pi over 3 is √3 over 2, and sine pi over 4 is √2 over 2. If you multiply this together, you have √2 over 4 plus √6. You multiply the radicands here, 3 times 2, and then 2 times 2 in the bottom, 4. And as a combined fractional expression, we have √2 plus √6 over 4. And that's your final answer, option letter D. All right, let's take a look at question number 3. We're to find the identical expression for the following: cosine square x times tan square x plus 1. So we're going to be making use of multiple identities here. First of all, let's take a look at this identity right here, tan square x plus 1. If you think about your Pythagorean identities, do you remember what tan square x plus 1 is? From the Pythagorean identities, tan square x plus 1 is equal to secant square x. So if I apply that here, I'm going to have cosine square x, let's write that again, cosine square x times tan square x plus 1 is equal to cosine square x. Now instead of tan square x, I'm going to write times secant square x parenthesis. Now we're going to use another identity known as the reciprocal identity. If I apply the reciprocal identity to secant, what do I get? You recall that secant x is equal to 1 over cosine x. So if I square this, I'll just simply square 1, which is 1, and then I'll square that also, okay? But the original identity is secant x is equal to 1 over cosine x. So if I apply that here, this will become cosine square x times 1 over cosine square x. Now you notice that I can reduce this, divide this by cosine square x, and that cosine square x, these two cancel out, and our final answer is 1. We can see that option C is our correct solution. Now let's take a look at question number 4. We are to find the values of the inverse sine of negative 1/2. And we have multiple responses here, multiple answers here. There are different ways we can do this. If we have memorized our reference angles, we can use that. We can use a unit circle, or we can also make use of the calculator. Okay, so I'm going to use a calculator to show you how to figure out what this is. Okay, so if we say some angle theta is equal to the inverse sine of negative 1/2. What does that mean? This follows that if I take the sine of both sides, I'll have sine theta, sine of theta is equal to sine of the inverse sine of negative 1/2. This follows that on the left side, sine theta is equal to negative 1/2. So all these theta values, if I take the sine of them and get negative 1/2, then they satisfy this equation, this expression right here. Okay? Alright, so let's write down the expression I'm going to be plugging into my calculator. I'm going to be looking for sine of 30 degrees, sine of 330, sine 30, sine 330, and then sine 390, sine of negative 30, sine of 150, and then sine of 210. Alright, I want to see which one yields negative 1/2 as an output. Now you have to be careful. You have to ensure that your calculator is in degree mode before you start your computations. Alright, so you can see DEG here with my TI-89 titanium is already in degree mode. If not, you just go to mode and change it. Alright, so let's go ahead and do this. We have sine of 30 is 1/2, no good. Sine of 330, negative 1/2, that's good. Sine of 390, 1/2, that's no good. Sine of negative 30, negative 1/2, that's good. So let's write down what we have so far so we don't lose track. So we have for 30 degrees is 1/2. This is negative 1/2 for 330, 1/2 for 390, negative 1/2 for negative 30. So bottom line, we know that this is good, and these two are no good. Alright, let's try the last two. Sine 150 and 210. Alright, let's look at 150. Sine 150 is 1/2, no good. And then sine of 210 is negative 1/2, and that's good. Alright, so this is 1/2 right here, which is bad, and negative 1/2. Alright, so our answer, solutions, are A, C, and our solutions are B, D, and F. Alright, so let's cancel this out. Solutions are B, option D, and option F. Another way you can do this is by using reference angles, as I indicated earlier. In order to do that, you have to be able to see that the reference angle for all these indicated angles are in fact 30 degrees. Okay? And then you know that all students take calculus, and the only quadrants where sine has a negative value is either in quadrant 3 or quadrant 4. So any of these angles that reside in quadrant 3 or 4 are going to be candidates by default, since they all have a reference angle of 30. All right, so 330, we know it's right here. Reference angle of 30 is in quadrant 4, so it's good. Negative 30 is right here also, so it's good. And 210 is right here, reference angle of 30. So we have 210 right here, and then we have 330 or negative 30. Okay, so since this is tan and cotangent, and this is cosine and secant, sine is going to be positive in these two angles right here. Okay, the other angles that we have, 30 is over here. This is 30 degrees, or is also 390. Sine is positive here, so that's no good. And then the other angle we have is 150, and that's over here. And we know that sine is positive here also, so that's why it's no good. So if you know your reference angles, and all students take calculus, you can also use that to determine the right solution. Okay, now let's take a look at question number 5. This is a multiple response question. We're to find the identical expression for the following: sine t divided by 1 plus cosine t. Okay, so let's write it down. Sine t divided by 1 plus cosine t. All right, so we know an identity that involves 1 and cosine. It's of the form 1 minus cosine squared t equals sine squared t. So can I multiply this by a certain factor to get this? The answer is absolutely yes. Think about your difference of squares. If you have a plus b, what do you multiply it by to get a squared minus b squared? You multiply it by a minus b, right? So if you have 1 plus cosine t, to get 1 minus cosine squared t, which is an identity we can substitute with sine squared t, because this is equal to sine squared t. What I'm going to do is I'm going to multiply the top and the bottom by 1 minus cosine t. 1 minus cosine t, 1 minus cosine t. All right? On the top, I'll have sine t times 1 minus cosine t. And on the bottom, you already know what you're going to have, right? If this is a plus b and a minus b, is going to be a squared minus b squared, or 1 squared, which is 1, minus cosine squared t. Okay? Let me show you the steps so that you can see what I'm talking about. So if you pull this out, first, outer, inner, last, you're going to have 1, first, outer, minus cosine t, inner plus cosine t, last, minus cosine squared t. So you notice that the two terms in the middle cancel out, right? So we now have sine t times 1 minus cosine t over an identity that we know, 1 minus cosine squared t. So 1 minus cosine squared t is equal to sine squared t. We can make that substitution here. So we have sine t times 1 minus cosine t over sine squared t. Okay, if we freeze for a minute, we'll find out that we've had a match. All right, option B is an identical expression to this expression right here. Okay, well, let's go ahead and simplify it a little bit more to see if we can get more matches. Let's see. Oh wait, we can break this down. This can be written as sine t times 1 minus cosine t divided by sine t times sine t. Okay, so these sine t's cancel out. So 1 minus cosine t over sine t is what we'll be left with. 1 minus cosine t over sine t. Okay, and this matches with option letter D. Okay, now all right, let's take a look at question number 6. Question 6 says prove the trigonometric equation, identify the property or identity used in each step. All right, so let's take a look at this. So first thing we can notice is that this quantity is being squared, cosine minus sine x. So this quantity is being squared, we can express it as cosine x minus sine x times what? Times itself. That's what squaring is, right? Times cosine x minus sine x minus 1. Okay? The question is it equal to 2 cosine x sine x? Alright? Now, what we're going to do next is distribute. Okay? So let's distribute this out. First, outer, inner, last. So if we do the first, it's going to be cosine square x, outer, minus cosine x sine x, inner, minus sine x cosine x, but using the reflexive property of multiplication, I can write that as write this as cosine x sine x. Okay, so that's inner, and then last will be minus times minus plus sine square x minus 1. Is it equal to 2 cosine x sine x? Alright, this right here is a distributive property that we just applied, so we can put it right here, distributive property. Okay, now let's simplify. The middle terms cancel out, so we're going to have cosine square x plus sine square x. Actually, they don't cancel out. We can actually combine them, right? So if I combine these two, it becomes negative 2 cosine x sine x minus 1. Is it equal to 2 cosine x sine x? Now, does this look like an identity that you can recognize, cosine square x plus sine square x? Absolutely, they add up to 1, right? So this is 1, 1, minus, we can now move this 1 right here. 1 minus 1 minus 2 cosine x sine x. Is it equal to 2 cosine x sine x? Okay? So what we did up here was just addition. And then here we use the Pythagorean identity. Or yeah, we can just call this operation subtraction. It's kind of related to addition, but what we did is we subtracted these two right here. So subtraction. All right, when we're combining this term and this term. All right, now if you combine these two terms right here, you notice 1 minus 1 adds up to 0. So you have negative 2 cosine x sine x. Is it equal to, kind of drop the minus, is it equal to negative 2 cosine x sine x, as indicated earlier? And the answer is yes. So that completes the proof. All right, let's take a look at question number 7. So question 7, if cosine theta is 3/4 and theta terminates in the first quadrant, find the exact value of tan 2 theta. Okay, so we're going to start by writing down what the identity for finding tan 2 theta is. This is going to be the double angle identity for tan. So we have tan 2 theta. There are different variations of them. The one I'll use, I'm going to use sine 2 theta divided by cosine 2 theta. All right, so to figure this out, I'll just find sine 2 theta and cosine 2 theta, and then divide them by each other to get tan 2 theta. Alright, let's start with sine 2 theta. To find sine 2 theta, I'm going to use the double angle identities for sine. And that is 2 sine theta cosine theta. 2 sine theta cosine theta. For this one, we already know what cosine theta is. Cosine theta is 3 over 4. So what is sine theta? Can we find it? The answer is absolutely. If we know cosine, we can find sine using the Pythagorean identity. So we can use the identity sine theta equals plus or minus the square root of 1 minus cosine square theta. So plus or minus the square root of 1 minus cosine is 3 over 4. If you square that, you get 9 over 16. And this becomes plus or minus the square root of 16 over 16 minus 9 over 16. When you look for the LCD of 1 over 1, subtract the numerators, you have plus or minus the square root of 7 over 16, which is equal to plus or minus root 7 over 4. Okay? Now, the question is it positive or negative? Well, since theta terminates in the first quadrant, what does that tell me about the sign of sine? So we'll make our nice little quadrants right here, coordinate system. And we know this is where theta resides, and we know this is where a is. A means all 6 straight functions are positive. So we can conclude that sine theta is equal to positive root 7 over 4. Okay? Now let's we now know sine theta is this, and then earlier it was indicated to us that cosine theta is 3 over 4. So we're ready to compute the value of sine 2 theta. So sine 2 theta is going to be 2 times sine theta, which is root 7 over 4, times cosine theta, which is 3 over 4. Okay, you have to be careful multiplying here. 2 and 3 are integers, so you multiply them together. 6, and the radical stays alone. Root 7 divided by 16. You can divide the top and bottom by 2. 2 is a common factor. So this becomes 3 root 7 over 8. So there goes the answer for sine 2 theta. Now let's find cosine 2 theta real quick, and then we'll be good to go. Cosine 2 theta is, there are 3 variations for cosine 2 theta, but since we're given cosine theta, I'm going to use the identity that is dependent solely on cosine for accuracy reasons. So I'm going to use the identity 2 cosine squared theta minus 1. So that's going to give me 2 times cosine theta is 3 over 4 square minus 1. Okay, so we have 2 times 9 over 16 minus 1. Simplify this. 2 goes here 1, 2 goes here 8 times. So we're going to have 9 over 8 minus 8 over 8, which equals positive 1 over 8. Alright, so now we have sine 2 theta and cosine 2 theta. So tan 2 theta, you have to be really careful here. Tan 2 theta is sine 2 theta over cosine 2 theta. Alright? Because we have sine theta and cosine theta, that's not what we're using here. We're using the sine 2 theta and cosine 2 theta to figure out what tan 2 theta is. Alright, so sine 2 theta is 3 root 7 over 8, and we'll divide that by 1/8. So to do this, we'll multiply the numerator by the reciprocal of the denominator. Okay, so the 8's cancel out. And our final answer for tan 2 theta is simply 3 root 7. Alright, so that's that. Alright, let's take a look at the last one, question number 8. We're to evaluate tan of the inverse cosine of 8 over x. Okay, so we can look at this argument of our tan function as an angle theta. Okay, so let's say theta is equal to the inverse cosine of 8 over x. Okay, so if theta is equal to the inverse cosine of 8 over x, what do you think these two measures are in a triangle in standard position? So let's make a triangle in standard position right here. I'm going to put it in the first quadrant. Okay. And let's say theta is in quadrant number 1, since there's no negativity here. So this is theta right here. So this is going to be your opposite. This will be your adjacent. And this will be your hypotenuse, right? Hypotenuse is opposite to 90 degrees. Opposite is opposite to theta, and then adjacent is the other side. Now you remember from SOHCAHTOA that there's a special relationship that cosine has, right? So cosine is the adjacent over the hypotenuse. All right. So here we know for a certainty that this piece right here is the adjacent, and this is the hypotenuse, a over h. Because inverse cosine and cosine work hand in hand. Let me prove that to you right here. If theta is equal to the inverse cosine of 8 over x, that follows that if I take the cosine of both sides, cosine theta is equal to 8 over x. So we can clearly see that this is adjacent, and this is hypotenuse from SOHCAHTOA. Okay? Alright, so the adjacent is a constant 8. The hypotenuse is a variable x. We have to find tan. What does TOA tell us about tan? Tan theta is opposite over adjacent, right? Over A. So we know what the adjacent is. We need to find the opposite. Now, how do we find the opposite? We just simply use the Pythagorean theorem, right? So I'm going to use the trig variation of the Pythagorean theorem. Adjacent square plus opposite square equals hypotenuse square. Alright, so let's plug in what we know. We know that adjacent is 8 squared. Opposite, we have no idea what that is. And the hypotenuse is x squared. Now let's go ahead and isolate O. O squared is equal to x squared minus 64. And then O is equal to the square root of x squared minus 64. So that's our opposite right here, right there. Okay, so let's go ahead and put everything together. So tan theta, which is equal to, we remember what we call theta, right? Theta is this expression right here, which is tan of the inverse cosine of 8 over x. That is equal to opposite over adjacent. Our opposite is root x squared over 64, and our adjacent is 8. Alright, so that goes our final answer. X squared, the square root of x squared minus 64 divided by 8. Okay, so that's that. Thanks so much for taking the time to watch this presentation. You can feel free to subscribe to my channel, and please post a comment to let me know what you think about this clip. More clips can be found on mathgoodserve.com. Thanks again for watching, and have a wonderful day.